We will continue with the next part of our discussion with Zener diode. Okay, Zener diode is a heavily doped special purpose junction diode. It is a heavily doped semiconductor diode which is designed to operate in reverse bias mode only. Okay, so Zener diode is a specially designed heavily doped semiconductor, and this is a symbolic representation of Zener diode, symbol of Zener diode, slightly different from that of normal PN junction diode. Okay, so it's a heavily doped one. And the Zener diode characteristics, that means it is designed to operate in reverse bias mode only. So the heavily doped nature of semiconductor, I mean this particular Zener diode, brings about lot many peculiarities with the diode. That means because of the heavily doped, that means lot many charge carriers will be present in this particular junction diode, and as a result width of the depletion region will be very small. It is less than 10 power minus 6 meter, and since the width of depletion region is very thin, as a result the electric field will be very high in the junction of the order of 10 raised to 6 volt per meter. Okay, so thin depletion region makes the electric field very high in that particular junction, and it is always operated in reverse biased mode. Okay, so since it is operated in reverse biased mode, we know that the reverse biasing, in reverse biasing the applied voltage will be supporting that potential barrier or the potential which is already present in that nearby the junction. So here already the junction is having a very large electric field, and in addition to that we are giving a reverse bias voltage. Okay, so a small voltage or small applied reverse voltage will be sufficient enough to make lot many electrons free from the host atoms of the p side of the diode. Okay, that means if from the p side of the Zener diode, okay, lot many electrons will be becoming free, giving rise to same number of holes in that region. So large number of charge carriers will be produced, and that is known as internal field emission or field ionization. With the electric field becoming very high, that particular region or the material become ionized. That means electrons become free, creating holes. So large number of electron hole pairs will be created in that region, giving rise to large current during that situation. This is what is shown here. The breakdown voltage, the Vz is known as the breakdown voltage of Zener diode, that is Zener voltage. It is also named as Zener voltage. Zener diode is always operating in reverse biased mode. So the reverse voltage versus the current gives a plot like this. Up to Vz, there is a very small amount of current in the circuit, but still it is in microampere range. But after Vz, that means once the breakdown happens, there will be large number of charge carriers produced in the particular junction, and as a result the current, the reverse current increases very rapidly even without even with a minute change in the reverse voltage applied. So here the reverse current is in the microampere range only, but still it will be increasing very sharply once the breakdown happens. So using this property of Zener diode, that means Zener voltage, once the voltage crosses, the applied voltage crosses Zener voltage, you can see the current increases without any change in the voltage. Okay, this property of Zener diode is having very important application. So this Zener breakdown, that means as we mentioned, the thin depletion layer develops high electric field. So the applied reverse voltage will be making the breakdown of the region, producing large number of electrons and holes. Okay, that is named as Zener breakdown or Zener voltage. And the main application of Zener diode is voltage regulator. Okay, voltage regulator, that means we have to make or keep the voltage steady. Okay, so voltage across Zener diode in the breakdown region is almost constant. That's the main property which we are using or which we are applying to use a Zener diode as a voltage regulator. And here this is the circuit which we use for voltage regulation purpose. Here you can see a series resistor Rs is connected to the Zener diode. A resistor Rs is connected to the Zener diode in series. Okay. Now the unregulated voltage is given to this particular combination, series combination of RS and Zener diode, and there is output voltage which is taken across the two ends of the load resistance. So here, since the Zener diode is having the peculiarity that once it reaches the breakdown, the voltage across the Zener will not be changing, it is all constant. Okay, so whatever changes happen in the input voltage, input unregulated voltage, that will not be affecting the voltage across the Zener. Okay, so in the output, that means across the RL, we will be always getting the regulator voltage Vz, because RL has been connected parallel to the Zener diode. So the same voltage, constant voltage, we will be able to get across the load resistor also. Okay, so whatever changes happening in the input voltage, that means whether it is increasing or decreasing, any increase or decrease in input voltage will be affecting the voltage across the RS only. Okay, voltage across the RS only will be changing, but the voltage across Zener remains constant. That is a particular property of Zener diode in the reverse bias mode. So you have to connect here in reverse bias mode, keep in mind. Clear? So voltage regulation by Zener diode, very important topic. The circuit diagram as well as the explanation. Okay, I hope it is clear to all of you. Now we have another category of this PN junction diodes. They are PN junction diodes only, but they are also designed for certain special purpose. So optoelectronic junction devices. These PN junction devices here, as the name indicates, optoelectronic. That means it is having some relation with the light, isn't it? So here the charge carriers are produced by the light energy or the photons. Okay. So here we want to discuss about optoelectronic junction devices like photodiodes, LEDs and solar cells. So these three optoelectronic devices we will be discussing hereafter. So first one, photodiode. It is also called a photodetector or photosensor or light detector. Okay. And from the symbol of the photodiode, it is clear that the light is falling onto the photodiode or the junction diode, and that means the photons are giving the energy, okay, to the junction, and as a result there can be some changes happening in the circuit that we will be discussing. So here this is a symbol of photodiode, and here one thing, photodiode is also operated in reverse bias mode. Okay, keep in mind, photodiode is also operated in reverse bias mode, and light energy is allowed to fall onto the junction. And this is what is happening. So the junction of the device is illuminated with light. That means photons will be allowed to fall on the junction. And this photons means is light energy. This light energy will enable the electrons to become free from their bond. Okay. So electrons become free means correspondingly holes also will be generated. So electron hole pairs will be generated. And this production of additional charge carriers because of the photons incident on the junction will produce additional current in the circuit. Okay. So it is already connected in reverse bias mode. So there will be that drift current which is present in microampere range. Okay. So that drift current, or initially there will be a small current present in the circuit, that we will name it as dark current. That means in the absence of light, even in the absence of light, there is a small current in the circuit named as dark current. But once we illuminate the junction with the light, then there will be increase in the current in the circuit, reverse current in the circuit, and this increase is only because of the new charge carriers developed or produced by the incident photons. So this is a characteristic curve of photodiode. As you can see, as the intensity of the light falling on the diode increases, the current also increased. It is in a reverse biased mode. Okay. So with the intensity, the current strength also increases. Next is light emitting diode. As the name indicates, it is emitting light. Okay. So from the symbol also it is clear that the diode or junction will be emitting light. So how it is able to emit light? Let us see. So PN junction, that means P region having holes as the majority carriers, and N region having electrons as the majority charge carriers. And when we fuse these two such regions, okay, this particular diode will be heavily doped. So there will be lot many charge carriers present in this particular region, and when we forward bias this diode, these charge carriers, majority charge carriers will be diffusing across the junction, and they will recombine, electron will recombine with the holes, okay, and thereby they will release energy in the form of photons, okay. So you have to keep in mind, light emitting diode, they are operated in forward bias mode, and here the photons, I mean the light is produced by the recombination of electrons and holes nearby the junction, and the color of light depends upon the particular energy, that means band gap energy of the semiconductor material. So the type of material, based on the material we can change the color of LED also. So visible LEDs, for having visible LEDs, the semiconductor used must have a band gap from about 3 electron volt to 1.8 electron volt, because within that range only we can have the VIBGYOR or visible light. Example, gallium arsenide, that will be emitting infrared, that means IR, infrared LEDs which we use in our remote controls and all, they are made of gallium arsenide. Another one is gallium arsenide phosphide. So using that we can have LEDs of different colors by changing the concentration of each atom. We can have LEDs of different colors. So the VI characteristics of LED is shown here. It is all similar to the VI characteristics of forward bias diode. Okay, forward bias normal PN junction diode, that is silicon or germanium diode. But here you can see different colors are having different, slightly different threshold voltage. Okay, almost the curve is having identical shape, but the threshold voltage differ for each color. Now LEDs are having lot many advantages compared to our normal incandescent bulbs. Okay, as we mentioned in our introduction part, we are having we have replaced the normal incandescent bulbs with the LEDs in our homes. Okay, so LEDs have the following advantages. They have a low operational voltage, less power, fast action, no warm up time is required, long life, it is reliable, and fast on off switching capacity. So the advantage is very important for LEDs. Next one, solar cell, another optoelectronic devices. Solar cell, that also we just introduced in the introduction part. Solar cell. So already we know that solar cell is able to convert solar energy into light energy. Okay, it's a photovoltaic device. So solar light falls on the PN junction and generates EMF, or that is electromotive force. That is there will be a potential developed because of the solar energy. And solar radiation is incident at the junction. Junction area should be kept transparent so that light can fall, and it is kept much larger for more power generation. Okay, and here you can see in this figure the solar cell is not biased compared to photodiode or LED. Photodiode we seen it is operating in reverse bias mode. LED it is operated in forward bias mode. But here solar cell, there is no bias at all. Simply solar energy is falling onto the junction and there will be EMF developed. Okay, there is EMF developed in the junction. So the working of solar cell, that is how the EMF develops, that depends upon three main processes: generation, separation and collection. Okay, that means generation means when the solar energy is falling onto the junction, there will be electron hole pairs generated because of the energy after absorption of the solar energy. The electrons become free, and as a result holes and electrons are generated nearby the junction. And separation, because of the junction, that means the barrier potential of the junction, this generated charge carriers will be separated to the two ends and they will be collected to the two regions of the diode, I mean the solar cell. And when we are connecting any external circuit across these two terminals of the solar cell, we are able to operate any lamp or any device, something like that. Okay, so it's actually a cell only which is providing voltage or potential difference. So three main processes, basic processes: generation, separation and collection. Okay, and the solar cell will be having metallic contact at the top and bottom surface. Top surface, it will be in the form of finger electrodes, because light should be able to reach the junction, and at the bottom surface it will be there will be a back contact of metal, and across the two contacts there will be an EMF developed. Okay, and solar cell VI characteristic curve, as you can see, this curve is coming in the fourth quadrant, because we know solar cell is the cell. That means it is actually developing a potential difference. Rather, in the case of photodiode or LED, or the other case of PN junction diode, where we have already applied the bias, external bias. But here there is no biasing given to the solar cell. Rather, it is developing the potential difference and it is applying it to us, isn't it? So, the particular VI characteristic of solar cell is coming in the fourth quadrant, because it shows that solar cell is not drawing any current, but it is supplying current to the load or to the external circuit. Okay, you can read there open circuit voltage and short circuit current. Open circuit voltage means when the circuit is in the open state, we can have maximum voltage across the terminals of solar cell, and when we connect the solar cell in the circuit, there will be current flow in the circuit, that is short circuit current. Okay, corresponding to that voltage. So this is the case with the solar cell. And solar cell applications, they are used in power electronic devices like satellite, space vehicles, that already you know, and also in calculators we are having solar cell. And for designing solar cell, the material selected should be based on certain criteria. That is, band gap should be between 1 electron volt and 1.8 electron volt, and it should have high optical absorption and high electrical conductivity. Again, the availability of raw material and also the cost. All these factors should be taken into consideration while selecting the material for solar cell designing. Okay. So, in this chapter, we have discussed about the semiconductor materials, their importance, the band theory of solids, right? The type of semiconductors, intrinsic, extrinsic, and how a PN junction diode is formed, and how a diode can act as a rectifier circuit, isn't it? And then we dealt with the case of Zener diode, how we can use Zener diode as a voltage regulator, and different kinds of optoelectronic devices like solar cells, LEDs, photodiodes, etc. So, I hope all of you have understood the concepts clearly. Read your textbook thoroughly and try to explore more about semiconductors, because they are very, very important in our day-to-day life. Thank you all the best, dear students.